Hello everyone. So today's pre-lecture tutorial is going to be an overview of what we call the kinetic molecular theory. Now, the kinetic molecular theory is essentially a collection of postulates that we use to help us understand gas behavior, and there are some fundamental relationships that can be derived or modified based on our understanding of the kinetic molecular theory. And so the first step really to implementing the kinetic molecular theory is to envision a gas as a collection of particles, much like the one shown in this figure. Now, notice that the figure is labeled that this particular system, which contains a collection of gas particles, is at 0 Kelvin. Now that's important because basically at 0 Kelvin, all motion stops. And essentially the kinetic energy of everything within the system would be 0. However, if we were to increase the temperature as shown in this simulation, basically our temperature right now is at 50 Kelvin within the simulation, you'll notice that the gas particles do begin to move. And the greater the temperature, then basically the greater the speed of the particles and the greater the kinetic energy of the system. Well, this observation can be understood if we consider the kinetic molecular theory. And so to summarize, the kinetic molecular theory has several postulates, some of which are common sense and some of them which require a little bit of thought. The first two postulates here deal with the way the particles interact, or essentially their lack of interaction if we're considering a gas to be ideal, because that's the first postulate of the kinetic molecular theory, that essentially gas particles in an ideal gas do not interact with each other. And what we mean by do not interact is that they do not repel each other and they do not attract each other. Now, granted, when you have a collection of moving particles, much like we saw in the simulation that I showed a few seconds ago, obviously with so many moving particles actually moving randomly, then we are going to get collisions between those particles. And when those particles collide, we're going to assume that those collisions are elastic, meaning that when the collision occurs, there's no energy loss due to heat. Essentially, the energy in equals the energy out for each collision. Now, as we saw in the simulation, basically the particles do move constantly in random directions, not necessarily associated with each other, and some particles will move faster than others, but overall we can take an average velocity, if you will, of all of the particles in the system. And we'll discuss essentially what that makes the gas particles do in terms of their behavior and their collisions with one another, and also understanding a little bit about gas speed in general. And also, the final postulate, which we're going to be discussing in greater detail in this tutorial, is again this postulate that says that the average kinetic energy of the gas particles is proportional to the temperature. So basically, the higher the temperature of the system, then the higher the kinetic energy of the gas particles. So let's clarify some of these points in greater detail. As I said before, basically, when we consider gas particles, right, again, they don't all necessarily have to be moving at the exact same speed. And that's what this graph is showing. Essentially, from here to there, basically this portion of the curve represents gas particles that are slower than this velocity right here. Now, that velocity happens to be the most probable speed for gas particles. Notice that for this portion of the curve here, these gas particles happen to move faster than the most probable velocity. Now, it turns out there is a mathematical expression by which we calculate the most probable velocity. That equation is actually U most probable, which is the symbol for the most probable speed, is 2RT over m, where r is actually the gas constant in its energetic terms, which is 8.314 joules per mole Kelvin. Also, this m represents the mass of the particle, and the mass is actually expressed in kilograms. However, if you notice, there's also another velocity here that we need to pay attention to, and that's this speed, which is the root mean squared velocity. And essentially, the root mean squared velocity is actually the speed of a particle that has the same kinetic energy as the mean kinetic energy. So the speed of a particle having the same kinetic energy as the average kinetic energy of the system. So don't worry too much about how to derive the equations for the root mean squared velocity, which is actually the square root of 3 RT over m, using the variables the same as we would have calculated for the most probable velocity. The important thing to understand is that the most probable velocity is, again, just strictly a count of the velocity that corresponds to that velocity shared by most of the gas particles in the distribution, whereas the root mean squared velocity is actually more centered on, okay, which particles have the same kinetic energy as the average kinetic energy of the system, and then isolating that velocity. Now, if you notice, this particular figure was actually created for oxygen at 300 Kelvin. Now, the reason it's necessary to actually specify the temperature is that there is a temperature effect on the distribution of gas particle speeds. And mostly this is because, as we said earlier in the postulates of the kinetic molecular theory, essentially the average kinetic energy of gas particles is proportional to temperature. And that's a direct proportionality. So basically, the greater the temperature, then the greater the kinetic energy. And if you recall back to middle school science and possibly maybe a freshman science course that you might have taken earlier, if we think back to our elementary physical science courses, kinetic energy is 1/2 mv squared, or v represents velocity. Well, basically, if we have a greater temperature, which leads to a greater kinetic energy, then basically that means that my distribution of gas particles should shift to higher velocity. And if we actually track the most probable velocity, say going from 100 Kelvin, and this particular graph is for nitrogen, if we track that most probable velocity and we let the temperature increase to, say, 300 Kelvin, what we're going to see is that there is a definite increase in the most probable velocity from about, say, 250 meters per second to approximately just under 500 meters per second. Now, as it turns out, there's also a molar mass effect on particle velocity, because if we compare the most probable velocity for nitrogen, we said that was just shy of 500 meters per second. If we take a look at that graph we were looking at related to oxygen, notice that the most probable velocity for oxygen is actually less than 400 seconds. And that can be explained by molar mass, because the molar mass of oxygen is approximately 32 grams per mole, whereas the molar mass of nitrogen is approximately 28 grams per mole. So essentially what we're seeing is that particles that have less mass tend to have greater velocities. And this is actually shown in the following figure. Essentially, if you take a look, hydrogen, which is the lightest of our gases with a molar mass of about 2.016 grams per mole, by far has the greatest, most probable velocity. And notice that as molar masses tend to increase, then basically the most probable velocities tend to move towards slower speeds. Now, as it turns out, we can come up with a law that quantitatively relates molar mass and particle velocity, and it's called Graham's Law of Diffusion. Now, effusion is basically the movement of a gas through a small opening. Okay, now, essentially, it also applies to diffusion as well, which, if you recall from biology class, diffusion is the movement of particles from high concentration to low concentration. Okay, and the way that we can come up with this mathematical expression for relating particle velocity to mass is to think of having a mixture of gases at the same temperature. And if they're at the same temperature, then their kinetic energy should be the same according to the final postulate shown here of the kinetic molecular theory. So suppose I have a gas mixture, right? Let's call it gas A and gas B. Well, the kinetic energy for gas A, if I'm at the same temperature for both components of the gas mixture, should equal the kinetic energy of gas B. Okay, now, recall, kinetic energy is 1/2. For gas A, it should be the mass of A times the speed of A squared. Similarly, the kinetic energy of B should be 1/2 mass of B, velocity of B squared. Notice that in this equation, the factors of 1/2 will cancel. And let's actually put all the velocity terms on one side and all the mass terms on the other side. So that would mean the velocity of A squared divided by the velocity of B squared is equal to the mass of B over the mass of A. If I take the square root of both sides, then that means the velocity of A over the velocity of B is equal to the square root of the mass of particle B over the mass of particle A. And this expression right here is what we know as Graham's Law of Diffusion. Let's put it into practice and see it in action and see how we deal with those types of problems. Suppose that I have a gas that I don't know exactly what it is, but I can measure its effusion rate. So it moves through a small hole at a rate of 4.73 times 10 to the negative 4 moles per second. Methane, which is actually another component in that same gas mixture, let's say, it effuses at a rate of 1.43 times 10 to the negative 3 moles per second. Suppose I want to find out what the molar mass of gas X is. Well, according to our relationship that we just derived, basically the velocity of X over the velocity of methane should equal the square root of the molar mass of methane divided by the molar mass of this unknown gas particle, particle X. If I plug in, then I would plug in my rates, 4.73 times 10 to the negative 4 moles per second divided by 1.43 times 10 to the negative 3rd moles per second. And that's going to equal the square root of the molar mass of methane, which is about 16.04 grams per mole. And I'm going to divide that by the molar mass of particle X. If I square both sides, okay, square that, I'm going to get that equal to 16.04 grams per mole over the mass of X. if I were to solve this expression for the mass of X, I should get about 146 grams per mole. Now, in the next pre-lecture tutorial, I'm going to talk about how we relate the kinetic molecular theory to understanding gas behavior and also to understanding when gases behave more ideal or less ideal. But for now, read through the section of the book related to kinetic molecular theory and Graham's Law of Diffusion, work on the follow-up assignment, and we'll discuss it in greater detail tomorrow. All right, have a good night. See you then.